iXblue component solution for quantum physics. As you all know, modern society relies heavily on private communications. Among the many activities that depend on it are e-banking, e-health, or secure government communications. Modern encryption techniques used to establish privacy have limitations as they rely most often on the supposition that an eavesdropper has access to a limited computational power to reverse engineer the key. Eventually, and with time, this will become less and less secure. Quantum key distribution is a secure solution guaranteed by the laws of physics. Indeed, a spy trying to intercept the key can be detected before the message is even sent, since a measurement by the eavesdropper would modify the information and allow detection by the recipient. The beauty is that QKD can be implemented easily on existing optical telecommunication systems, either via optical fiber or free space communication links between satellites, for example. So here we illustrate QKD with a CV-QKD setup using standard telecom components, a laser, electro-optical modulators, and a coherent receiver. The information is encoded in both the amplitude and the phase of laser pulses using iXblue solutions. You can see two amplitude modulation blocks, AM1 and AM2, that are cascaded with a phase modulation, PM1. The first amplitude modulator, AM1, is used to generate a very short soliton-like optical pulse. The second amplitude modulator, AM2, is used to randomize the optical pulse amplitude. And finally, the phase modulator is used to randomize the optical phase. So let's explore the electro-optic modulator performance required in such a setup. We'll start with the amplitude modulators. Again, we're looking at securing communication between data centers, satellites, buildings, and one can use standard telecom wavelengths that include 850 and 1310 for datacom, and 1550 nanometer, which is the standard telecom wavelengths. It seems actually that satellite communication is now adopting 1550 as well to leverage the development done by the telecom industry. But for the folks who want to do this at 1 micron, we can also provide a solution there. Most importantly, we have space-grade version in every wavelength range. Now, for the first amplitude modulator, AM1, the goal is to generate very short optical pulses. So the EUM needs to provide fast rise and fall times, which requires a wide electro-optic bandwidth. Also, the pulses need to have a good signal-to-noise ratio and an optical contrast or optical extinction ratio that should be more than 30 dB or more. For the second amplitude modulator, AM2, we would want to minimize the optical insertion loss and provide good linearity of the optical response to set the desired amplitude level with good repeatability and stability. For the phase modulator, PM1, we want to preserve as much optical power as we can and minimize the optical insertion loss. Also, in order to apply random phase to an optical pulse, the modulator needs to have a relatively wide bandwidth. So let's see what we can propose. We'll start with the amplitude modulators. So for each wavelength band, we have a dedicated modulator with an optimized wavelength size to match the wavelengths of operation. It's the waveguide size, right, to match the wavelengths operation. We have also optimized the design of the Y junction of the Mach-Zehnder interferometer to minimize optical insertion loss. We call that the magic junction. This is a patented design that allows us to consistently minimize the optical loss when splitting and recombining the waveguide. At 1550 nanometers, our modulators feature an insertion loss of 3.5 dB typical. Our amplitude modulators also provide excellent optical contrast, 33 dB typical at 1550 nanometers, and can be selected for optical extinction ratios of 40 dB or more if necessary. Note that if you want to take advantage of the optical contrast provided by our EUMs, you will also need a good bias control. Our modulators feature a low DC drift that will make it easier to stabilize. We favor X-cut design to provide better stability, and we also provide separate RF and DC electrodes. As far as rise and fall times, our modulators feature less than 20 picosecond of rise and fall time, even for the 10 gigahertz version at 1550 nanometers. This is because the bandwidth of our MXER LN10 is around 14 gigahertz, and the S21 is relatively flat. In terms of power handling, optical power handling, it may not be that critical for QKD, except maybe for pulse generation of the first AM1 amplitude modulator. We specify 100 milliwatt in the C-band. Note that the optical power handling of our modulator 850 is 60 milliwatt, which is the highest in the industry, and it's also the most stable modulator out there. Now let's move to the phase modulators. Again, phase modulators need to be tailored to the operating wavelengths in regards to the waveguide size. We do provide a low insertion loss for the phase modulators, such as less than 2 dB in the C-band, which is fairly good. Here we favor the ZCAT design because we want to minimize the VPI of the phase modulator. In the near infrared, though, we still use XCAT because it provides better stability. So as an example, the MPZ-LN01 has a VPI of 3 volts at 3 gigahertz, and in fact has a 4 to 5 gigahertz bandwidth. So it may be a good fit for your application. The 10 gigahertz version has actually a bandwidth of 16 gigahertz and a VPI of 6 volt at that frequency. Also, I would like to point out that the S11 of our modulators isn't generally very low because we want to maximize the RF to optical conversion efficiency. Finally, and this is an important point, we now have a DC coupled phase modulator and we provide a DC input to the phase modulators as well. This will help you mitigate residual amplitude modulation. We have an application note about that, and will also help correct for pyroelectrical effect, especially in ZCAT designs that potentially add phase noise to the signal. So now let's move to the RF, because in order to generate a good signal, you also need a good RF amplifier and obviously a good signal generator. So for optimal results, we have developed the DRVE10MO. VE stands for versatile. This driver can be configured to match your needs and can operate as a limiting amplifier for pulse generation or as a linear amplifier to generate multi-level signals.